and then the final first thing Monday morning. Because if you studied and you had questions and things, there really wasn't much of an opportunity to come and get a clarification. So that's why I stuck this lesson in here. And then Monday we will have our review, and Wednesday morning we'll have our final. Okay? So, or not final, our exam. We don't even have a final in this class. No, we do not have a cumulative final. It's just our exam number 3. Okay? So it's going to be primarily, the third hour exam will be on heat exchangers and radiation. Okay? This material today is not included on the hour exam. Heat exchangers are ubiquitous. They're everywhere. They're in everything we do. We're constantly exchanging heat. Give me an example of some heat exchangers right around you.
Radiators.
Right behind you is a unit, that is called a unit ventilator. It's called a unit ventilator because not only does it provide heating or cooling for this space, but it also allows outside air to be brought in sufficient quantity to meet the codes for fresh air. As a matter of fact, you may not have even noticed, but these rooms are a lot fresher since we've had these new units put in. Because in most cases, the unit ventilators that were put in the 60s when this building was built, 60s and early 70s, had the outside ventilation doors wired shut for one reason. So we weren't getting much fresh air. That's one example. What's another example of a heat exchanger?
Radiators.
Pardon me?
Car radiators.
Well, I'm exchanging heat with the environment, but that's not a mechanical device. Car radiator is a good one. Transmission coolers is another example. Air conditioning condenser in the car is another example. In your dashboard are your coils for providing the heating and cooling space to your space. All right. The heating water comes off the engine, and the air conditioner runs a refrigerant that runs from the air conditioning compressor in their car in through the little evaporator coil in your dashboard, and then back to the condenser, which is mounted typically in front of the radiator. Okay? So if your car has 2 radiators, one's the air conditioner condenser, and one is the radiator itself. Sometimes they're side by side. I've seen it happen too. Okay? All good examples. They're everywhere. They are everywhere in everything we do. So let's take a look at the types of heat exchangers that are most common that we're going to study. The first category, the category we're going to examine today, are concentric tube heat exchangers. And they are just that. They consist of concentric tubes. And if you're flicking through your memory to... What happened to Scott?
He's just standing outside.
He just left.
His sailing practice.
I know he has sailing practice. I did not mark him absent.
Oh, you gotta change that.
Yeah, you said he was here, but he was never here.
Yeah,
He was never here. Okay, concentric tube heat exchangers are, just as we say, made up of concentric tubes. And that is a tube inside a tube. So what happens is you have one fluid flowing on the inside of the inside tube, and then you have the second tube flowing in the annulus area constructed between the outside tube and the inside tube. Okay? Now there are 2 ways that these heat exchangers are constructed, or operate properly is a better way of putting it. One is those that have both flows going in the same direction. So those are known as parallel flow, concentric tube heat exchangers. And the other is counterflow heat exchangers, when the flow goes in the opposite direction. And the British have 2 different ways of saying that when we get to the heat exchanger lab coming up here after the test. And don't worry, it's not another lab. it's a lab, we go up and we do a demonstration, what have you, but all you gotta do is do a homework off of it, so it's not a big deal. That's one type of heat exchanger, two-sided tube, centric tube. The second is what we call cross-flow heat exchangers. And the most common case of cross-flow heat exchangers is your air conditioning condenser that you see outside your house. And what is the cross-flow? Well, inside in the little tubes is the refrigerant flowing, and air is being drawn across or perpendicular to those tubes and through. And when the air is separated by little fins like this is what we call an unmixed case. And when one or more of the fluids is allowed to flow pretty well as it wishes, that's called a mixed case. By far, unmixed cross-flow heat exchangers is the most common, such as you see in your car radiator. Okay? Now, the last one, which is a very big category, are shell and tube heat exchangers. And a shell and tube heat exchangers, and we're going to actually see all of these in this course before we're done. A shell and tube heat exchanger is a big shell, and it can sometimes, a big shell and tube heat exchanger can have a shell that is 2 or 3 meters in diameter, okay, and maybe 4 or 5 meters long. You'll see shell and tube heat exchangers that would go up the length of this room and be from diameter from top to bottom. And inside those will be literally hundreds of tubes which run down and out. And the number of times that the tubes run down and then back, you go down once, that's 1 pass. If you come back, that's 2 pass. You go down again, that's 3 pass, 4. You get the idea, okay? They usually go 2, 4, 6, or even 8 pass heat exchangers. And so shell and tube heat exchangers are categorized by the number of shells and the number of tubes. The most common one we'll see is a 2-pass single shell heat exchanger. Double shell heat exchanger is really like two shell and tube heat exchangers connected to each other. All right, so those are the general categories. Your book has some excellent pictures of them. We are going to see more pictures of them before we're done. Right now, that's the explanation I'll give you of those types. Now we need to talk a little bit about heat exchanger design considerations. All right, the first thing that we need to do when we're designing a heat exchanger is to determine how much heat we want to exchange. And sometimes we don't even know the answer to that. Rather, we'll know things like we have 2 fluids involved in the exchange, and we want to heat one fluid from one temperature to another. Okay? So, how much of the other fluid do we need? And how are they going to come together? How are we going to exchange that heat? All right? So we'll be asking questions of that nature. And there are certainly a lot of mechanical considerations. We need to decide the size and configuration. And sometimes we're not actually designing. Sometimes we're given an old heat exchanger and we're told to see if it'll work in an application. As a matter of fact, no kidding, I had a student years ago went to work for Electric Boat, and he had graduated and called me up or sent me an email. And he was so excited because he was working for Electric Boat, and they had given him a small, submarines are full. Electric Boat's in Groton, Connecticut, if you don't know. And they build the new submarines, and submarines are jam-packed full of heat exchangers. He was so excited, he said, because he got a small concentric tube heat exchanger, and his boss said, go figure out if this application will work for what, blah, 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 blah. And he says, I knew exactly what to do. I was very happy, and my boss is very happy. So, very practical type of stuff that we're learning here with heat exchangers, okay? So, sometimes it's not that you're going to design it from scratch. Sometimes you're going to be given one, you're going to be asked, will it work? You can do that too. And then lastly, if you're designing it, you've got to manufacture it. And for those of you taking manufacturing with Dr. Palm, you know that that's a big issue. And also, you got to maintain heat exchangers. That's another issue. It's been more than one shell and tube heat exchanger which has been installed in a building, and then the building finished being built around it, only to discover that there's not enough room to extract the tube bank for cleaning. That's a big issue. All right. What's one of the classic automotive problems with design? Has Palm told you this? It was General Motors that did it. I can't remember now for the life of me which one of its divisions. That's right. They built an engine that you couldn't change the spark plugs unless you pulled the engine. So they discovered that after they had actually built, I don't know how many 100,000 of these cars. And so what they had to do was they had to give lifetime spark plug changes for free to the owners of the cars, because otherwise it was $600 or $1,000 to get your spark plugs changed. So manufacturing considerations are not inconsequential. They're really a big deal, okay? General Motors pulled a couple of boners. You know what the other thing they did? Back in the 80s, there was this real craze for diesel engines. So General Motors is a big company too, you know, they got a lot of smart people. So they had this the classic General Motors engine, probably the best General Motors engine ever made, was a 350 cubic inch engine with 4-barrel carburetor. That thing would hum, all right? All your muscle cars from the 60s and 70s had a 350 engine. 455 was good in the Firebird too, in the early 70s. So they wanted to come out with a diesel engine. And what they did is, they took the 350 block and said, we'll just convert it to diesel. And what happened? The blocks all broke. So they were constantly replacing them under warranty. And General Motors has never marketed effectively a diesel passenger automobile since. It just ruined the market. Another case of poor manufacturing and design. All right? So there's a lot more that goes into this than meets the eye. All right, so what we're going to focus on in today's class is, for the purpose of derivation, we're going to take the concentric tube heat exchangers. So let's take a look at how we design a heat exchanger. And we're going to start with a parallel flow concentric tube heat exchanger. Here's one tube. All right, and we're going to insulate this thing so that the only heat exchange that goes on is the heat exchange between the two fluids which are flowing through this heat exchanger. And so the inside fluid we will call M dot C, and that will be our cold fluid. And it will enter here, and it will exit over here, and it will be hotter. But it's still going to be M dot C. Okay? Up here, we're going to bring our hot fluid in, and it's going to exchange heat as it flows down and exits here. And if we were to reverse the direction of one of these heat exchangers, we'd have a concentric tube counterflow heat exchanger. Okay? That's all there is. As a matter of fact, in the demonstration you'll see in the lab, we are going to deal with the concentric tube heat exchanger, and by flip-flopping the little tubes and what have you, we're able to reverse the flow, and you can see the difference. All right, so this is our heat exchanger we're going to be dealing with. This is a concentric tube heat exchanger. And this is parallel flow. Okay? All right. So the first thing we can recognize from thermoanalysis is the heat transfer that takes place inside this heat exchanger has got to be equal to, if we want to say, how much heat does the heat exchanger exchange? Well, it's going to be the amount of heat given up by the cold fluid, or excuse me, absorbed by the cold fluid, or given up by the hot fluid. And that's assuming for a moment that we're looking at the magnitudes and not the direction. Okay? All right, so what do we have? Well, that means Q is going to be equal to m dot Cp of our cold fluid times the temperature of the cold fluid out minus the temperature of the cold fluid in. And that's got to equal the heat given up by the hot fluid, which is going to be m dot C sub P of the hot fluid times T of the hot fluid in minus T of the hot fluid out. And what you'll notice here is I've arranged these temperatures so that both of these are positive values. Okay? All right. And I think you'd agree with that. It's got to be that. Assuming we have it well insulated, the heat's going nowhere else. Okay? Now, we are going to, next step, find something called heat capacitance. Heat capacitance. The heat capacitance rate, C. That's large C, where large C is defined as m dot C sub P. Obviously, thinking ahead, you can have a heat capacitance rate for the cold fluid, you can have one for the hot fluid. Right? Okay. Now, at this point, we're going to take a moment and step back, and we're going to take a look at the two different techniques that we can use to design or size heat exchangers. So the heat exchanger analysis techniques. The first one, and the one that we're going to look at for the rest of today's class, is the log mean temperature difference technique, or LMTD, log mean temperature difference. The log mean temperature difference is typically considered to be the best method for designing a heat exchanger from scratch, where you know the mass flow rates of the fluids you have, or what you want to have, and you want to know what their temperature differences are. Okay? Obviously, even if you're constrained by how much heat a fluid can give off or absorb, and by its flow rate, if you make the heat exchanger bigger, you can exchange more heat by the end of the time it gets out. Or you can conversely make it smaller and not exchange as much. Okay? So, log mean temperature difference is typically best used for heat exchanger design. Okay? And that's when the fluid temperatures of the temperatures and flow rates are known. The second method, which we will examine next Friday when we return when we pick up the material again after the test, will be something called the NTU effectiveness method. This method can be used to design, but it is also very effective when you want to be able to predict the performance of an existing device. But it can also be used for design. And today, we're going to look at the log mean temperature difference. Okay? All right. So let's take a look. Okay. All right, first thing we're going to do is we're going to construct a thermal circuit. Just like we did on, what, second or third day of class. We're going to construct a thermal circuit. We're going to be dealing with this example right here. All right, so we want to figure out what are the resistances. We want to know what this heat transfer Q is. And we know that Q is going to be equal to the delta T of the fluids. Don't worry right now, you're getting a little more sophisticated than you were at the beginning of the course. You probably realize right now that the fluids don't stay the same temperature. But you want to know that heat transfer, which is going to be equal to, at any given point in the heat exchanger, a function of how the fluids differ in temperature, the driving potential, divided by what?
Resistance. Total resistance.
Total resistance. All right, and to do the total resistance, we're going to construct a circuit. Now, you just got done doing a homework problem that was very similar to this. And if we start from the hot fluid, we're going to have the resistance due to the convective coefficient of the hot fluid flowing over the outside of the interior pipe, correct? So that's going to be 1 over, and we'll call that, since it's on the outside of the pipe, H sub O, A sub O. We could also call it hot, if you want. But then you get too many H's here, so we'll just go with the O's and the I's. All right, then we have the resistance due to what? Gio?
Material.
Correct, the pipe. And do you recall off the top of your head what that is?
Something K.
Natural logarithm of R2 divided by R1 over 2 pi K L, the length. Okay. All right, and then we have the last one, and we could express this in terms of the area would be what? Pi d, no, careful. Some of you still challenged with that one. Pi d O L. The perimeter times the length. Okay? So what's this over here? 1 over HI AI. And now you have all the tools that you need. You have all the tools you need to calculate the H's, and you can solve this problem. Okay? You can solve this problem. All right. So, this, by the way, and this is worth saying, is ignoring fouling factors. power plants where you have boilers and condensers, they have an unnatural fetish about fouling. And why is that? Because fouling costs them a great deal of money and requires taking boilers and/or condensers down offline to clean off the fouling. What is the fouling?
Corrosion.
Well, have you ever boiled a teapot? Not exactly corrosion. Have you ever boiled a teapot dry?
Yeah.
Well, what happens? It
Mineral
leaves that
deposits.
whatever chemicals are in the water on the bottom of the teapot. Well, that's constantly what's happening in a boiler and in a condenser, the same thing. So they're fanatic about it. They get huge efforts in all power plants. They treat their water so it's absolutely as neutral as can be. But still, 24 hours a day, 7 days a week, week after week, month after month, year after year, minerals do deposit on the surfaces of the heat exchange surfaces. And it gets to a certain point where it begins to affect the ability of the device to operate as designed. That's when, in the case of a big condenser, they have to take the condenser offline. You take the big plate off the front of the condenser, which is all bolted on, roll it to the side to get lifts and what have you, and then you extract the tube bundles, and depending on the cleaning technique, you might submerge the whole thing in an acid bath to do away with it. All right, and then they have brushes. Got neat thing, look, brushes. They run down the tubes. They can clean the inside of the tubes that way without taking them out. But if they got to take them out, literally, if the thing's not designed right, you can't take the tubes out because oftentimes they build these things. They build the buildings around the big condensers. That's a big issue. All right, somebody will be very upset at some point when they find they can't clean their condensers. So we're going to, in this course, ignore the fouling factors. Open your books up now to chapter 11 and turn to table 11.1 on page 675. That is a table with what we know as representative fouling factors. If you ever have occasion to be working in a design firm and you're designing a power plant, you will most certainly include representative fouling factors in your heat exchange devices. All right? Why? Because at a certain point in time, if you don't take these into consideration, they will diminish the ability of the device to exchange heat. So what you want to do is when the device is clean and brand new, it's going to work better than it does after 5 years. You want it to work after 5 years like it was designed to work. So you over-design it by including these fouling factors. These fouling factors are included as additional resistances in your network. It's that simple. Good example problem. We're not going to do it in here. There's not enough time to do everything. I'd like to, but we can't. So just know that that's in reality included in typical real design. All right. So having said all of this, we have the sum of our total resistance is going to be equal to 1 over H sub O A sub O plus the natural logarithm of the ratio R2 over R1 over 2 pi KL plus 1 over H sub I A sub I. And if we more often, we'll write this as 1 over U sub A, where UA is our heat transmission coefficient, and UA is equal to 1 over this term right here. Now, you did that in one of your homeworks, okay? And so you should have some feel for how that's done. One thing you got to be a little careful of, if you're designing a heat exchanger and you're working a problem, what you do is, typically you're designing the length, okay, for certain tube sizes. So how would you break this out? You do it by putting here pi d O L, over here pi d I L, And then you can group all these terms and multiply them by L. And you can break the common dimension of L out of all of them, okay? That's how you do it. All right. So, let's take a look now at the two cases that we can encounter. And we're going to determine delta T. All right, we have our total resistance here. Now we have to focus in on this term right here. Now, remind yourself of what you've already seen. Let's take a look at parallel flow to begin. All right, this is our temperature, and this is our distance x as we flow through the tubes. All right? This will be point 1 where the fluids enter. Over here will be point 2 where they leave. All right, now in a parallel flow, our hot fluid is going to come in hot, and it's going to be as hot as it's going to be, right? Because it's going to be getting enough heat. Our cold fluid is going to come in as cold as it's going to be. So what we see in this case is two curves that look like this. Where this is your hot fluid in, this is your hot fluid out, this is your cold fluid in, and this is your cold fluid out. Now theoretically, if we build a long enough heat exchanger, this would narrow down to what? 0. Okay? It would pretty well come down to 0. But we never do that, of course. There's all sorts of different reasons. This is known as delta T at 1, and this is known over here as the delta T at 2. And the fact of the matter is that there is no linear relationship here. One is cooling, one is being cooled, one is being heated, and the delta T is constantly changing across the entire heat exchanger. So the amount of heat that's being driven is changing as well. Okay? So this is for a parallel flow case. Now, what we have here is this area in here is representative of the delta Q. Proportionally, is representative of the delta Q at any given point. The amount of heat transfer that's going to occur between some point here and some point here is represented by this area between these two curves. Of course, influenced by the total resistance. Okay? Which is going to be more or less the same. All right. So what we have here, and this is worth noting, is delta T1, in this case, is equal to TH in minus T cold in, and that's going to be equal to TH at 1 minus T cold at 1. And delta T2 is going to be equal to TH out minus T cold out, and that's going to be equal to TH at 2 minus T cold at 2. All right, so that's for the case of parallel. What does our delta T look like for counterflow? Well, we'll draw the same diagram. Where 1 is the inlet, 2 is the exit, and now we have the hot fluid coming in and it's being opposed by the cold fluid leaving. So the hot fluid is going to be as hot as it is, and the cold fluid is going to be as hot, as high as it's going to be. So what we end up with is curves that look like this. And these are nonlinear curves, and while the temperature difference does not change as much as over here, they're not necessarily, it's not a constant temperature process throughout, okay? So you have here your your hot fluid in. Here you have your hot fluid out, and it is flowing in this direction. Over here, we have our cold fluid in, and up here, we have our cold fluid out. This is still delta T1, and this is delta T2. But now, these are defined a little differently. Delta T1 is equal to our hot fluid in minus our cold fluid out, but that's still equal to TH at 1 minus T cold at 1. And delta T2 is equal to TH out minus T cold in, but that's also still TH2 minus T cold 2. Okay? Pretty simple. All right. Now get a little mathematics, but it's pretty easy mathematics. So, in general, we can say that delta T is going to be equal to difference between TH and TC at any given point in the process, okay? Regardless of which way it's going, at any point there's a delta T here, there's a delta T over there. We'll worry about identifying it in a moment. But this is a generally true statement. All right, or we're going to say that delta, that the differential change of delta T will be equal to the change in the hot temperature minus the change in the cold temperature, the differential change. All right, now we're going to examine the heat transfer. Right? So we have Q is equal to m dot Cp C times T cold out minus T cold in. But Q is also equal m dot C sub P H times the temperature of the hot in minus the temperature of the hot out. And both of those are positive quantities. Or, if we write these in differential form, we can say dQ is equal to Cc, that is the heat capacity of the cold fluid, times the change in the cold fluid, dTc. Or we can rewrite this as dTc is equal to dQ over C sub C. And similarly, dQ for the hot fluid is going to be equal to CH times the differential change in the hot temperature. Or we can say dTH is equal to dQ over C sub H. Keep in mind that these dQs are identical, okay? The heat given up by one is the heat from the other. Or we can now go back to this equation, and we can say that the differential of the delta T is equal to minus dq times 1 over ch plus 1 over cc. It just requires a little algebra to get from here to there. All right? Because this is equal to this, and we're going to substitute in this and this. Okay? All right, now. Oh, there's one. Hang on. Oh,
Yeah, big racer.
no, this is right. It's just I made one mistake right here. And really, it's okay. This is going to be out, and this is going to be in. So we're going to leave these both, and then we're going to put a negative sign right there.
Is that also?
Hang on. So this is negative. This is out and in. I'm going to re-switch these. Okay? And then, so this will be negative, and this will be negative, and then this is negative. Okay? And that works. All right. This is a good place to stop. When we come back on Monday, I am going to, here's how we're going to work Monday. Monday, I've got